Here's the idea for problem 203, number 3. We're looking for a point in space, such as, I call it point P1, where the electric field due to this one and the electric field due to this one, due to charge particle Q1, I'll call that E1, and the electric field due to Q2, call that E2, add up to 0. Now, right off the bat, you can see that there's no way you can get these two vectors to add up to 0 unless they both lie along the same line. And the only way they're going to lie along the same line is if the point at which we're calculating the electric field is somewhere on the x-axis. So let's try over here. Then E1 would be, I'll call this point P2. P2 E1 is going to be to the left, directed away from the positively charged particle, and E2 is to the right. Now, we got a shot at it because these two are not only along the same line, but they're in opposite directions to each other, so they tend to cancel out. This is E2. The electric field due to this charged particle that's got a negative charge, where the value of the charge is Q2. Now here's the thing. E1 is going to be bigger than E2 at all points to the left of the origin because it's got both things going for it. One, it's closer, and the closer you are to a charged particle, the greater its electric field. And two, the charge is greater. You look at the values of the charge and you notice that the absolute value of Q1 is greater than the absolute value of Q2. So for both reasons, E1 is always going to be greater than E2, so there's no way the two of them can add up to 0. So let's check a point like P3. In between, E1 will be to the right and E2 will be to the right at point P3. Again, the electric field is in the direction in which a positively charged particle would experience a force if you put it at the location such as P3, and a positively charged particle right there would be pushed to the right by Q1 and pulled to the right by Q2, so they're both to the right. So there's no way that those two electric fields are going to add up to 0 because they're both in the same direction. So our only hope is some kind of point like P3 at this point, where the electric field will be away from charged particle Q1 and toward charged particle Q2, E2. So yeah, it's possible that these two will cancel each other out. They're in opposite directions, and we have competing effects. E1 would tend to be greater than E2 because Q1 absolute value is greater than Q2 absolute value. But E2 would tend to be greater than E1 because we're closer to charged particle number 2. So yeah, it's quite possible that those two can add up to 0. Now we got to be careful what we mean in there. KQ over R squared. This distance for point 3 would be R1, the distance that P3 is from Q1, and this distance would be R2, the distance that the point in question is from charged particle number 2. We can say that R1 is equal to the distance between these two plus R2. So let's make up a name for the distance between those two. Probably not a good idea to use an R because that's our distance between a charged particle and the empty point in space, and we don't want to accidentally be putting that in there for the R in the denominator of KQ over R squared. But R1 is equal to D plus R2. And by the way, we're looking for a value of x. Let's just, that's the coordinate x. of the empty point in space, point P3, then I call it point 3, P3. So our answer is going to be an x value that I'll just call x, and given that R1 is equal to x, it's probably best to call R2 R1 minus D, so R2 is equal to x minus D. And then if I just say E1 plus E2 vector is equal to 0, means E1 times I plus E2 times I is equal to 0, or E1 plus E2 is equal to 0. These are just the x components, and that would be KQ1 over R1 squared plus KQ2 over R2 squared equals 0. You can work with absolute values of the charges if you want. I work with the actual charge, so I have a plus sign, but there's a minus sign inside the Q2. In other words, Q2 has a negative value, so I'm taking care of it that way. And then KQ1 over x squared plus KQ2 over x minus D squared is equal to 0. Just solve that for x, and you get the value. Make sure that x comes out to be bigger than 14 centimeters for it to make sense, because we assume that the point in question was to the right of Q2, but you solve that for x and you got it. So that's the idea on that one. I guess you want to make sure that you recognize what you're doing is calculating the electric field at an empty point in space, and put these electric field arrows on there and just explore what conditions have to be met in order for it to be add up to 0. And you don't want to just like start off the problem assuming, well, it's going to be on the x-axis and it's going to be to the right of point Q2. Explain how you arrived at that conclusion. Okay, let's call it a wrap for this video.